Hey, and welcome to the isoPoint training series. I'm Eric with Aktina, and today I'll walk you through how to analyze your Isocenter validation data. This video builds on a previous one where we covered how to measure an Isocenter validation dataset in detail. Let's dive in. Start by locating the Isocenter Validation Report within the Isocenter Validation dataset in the isoPoint software and double-click to open it. There are three key areas I want to focus on, covering the critical aspects of the report so you can read and interpret it like a true expert. The first section we'll cover is the beam's eye view graph on the second page. Since this is a beam's eye view reference frame, just like a traditional port film image, it represents the view looking straight down the collimator's axis. The most important thing about this plot is that it shows both the radiation beams superimposed over the collimator axes. This is a superposition of two datasets with a common origin. The beam axes are always shown relative to the marker location, and the collimator axes are always shown relative to the physical isocenter. If you placed the marker at the physical isocenter during the test, then these locations will align, giving you a common origin for this plot. This plot is packed with data, so let's break it down step by step. First, let's focus on the collimator axes. The collimator axes are represented by the color-coded X symbols. The first thing to notice is that the 0 and 180 degree axes are spread apart in the in-plane direction. The distance of that spread represents the magnitude of your LINAC's gantry sag. The collimator axes also reveal how accurately the collimator was positioned during assembly. If all the collimator axes are shifted either to the right or left, it means the collimator wasn't assembled correctly in the cross-plane direction relative to the gantry's axis of rotation. Ideally, they should be perfectly aligned with the y-axis in this plot. Additionally, the collimator axes can indicate whether there's any hysteresis in your gantry rotation. If you measured a 5-axis eye mark, then the 180 degree and minus 180 degree gantry axes should be very close to each other. If they're not, there may be mechanical issues with your gantry rotation. Now let's take a look at the beam axes, which are shown as circles with color codes matching the collimator axes. Ideally, each beam axis should be perfectly aligned with its corresponding collimator axis. However, there are three scenarios where misalignment can occur. If all the beam axes are shifted either toward or away from the gantry, it indicates an in-plane misalignment. If all the beam axes are shifted either to the right or left, there's a cross-plane misalignment. Both of these issues can typically be corrected with proper beam alignment, which we cover in separate training videos. The third type of issue occurs when the beam axes at different gantry angles are misaligned from their collimator axes by varying amounts and in different directions. This suggests a failure in the LINAC's beam alignment. Unlike the first two cases, this issue cannot be solved with simple in-plane or cross-plane global shifts and may require further investigation. When the beam and the collimator axes are all coincident, that means radiation isocenter has converged to physical isocenter and the LINAC is optimally tuned to reduced geometric errors. Of course, that's not the whole story, and we need to look at the couch behavior, which we'll do next. The third page of the report contains a couch plot displayed in the patient coronal plane, which is perpendicular to the couch's axis of rotation. This plot visualizes the marker shifts for each couch rotation with the origin set to the marker location at couch 0. Superimposed on this plot is the couch's axis of rotation measured using optical tracking. Remember that if the couch axis is far from the marker at physical isocenter, then we should expect a roughly circular motion of the marker as the couch rotates. If the couch axis is very close to the marker, then small marker shifts should be shown that represent the couch-bearing walkout, small unavoidable movements due to imperfection in the mechanical rotation. Pro tip, the location of the marker for each gantry angle in these plots does not depend on beam alignment or MLC accuracy or field-to-marker centers. Each marker location is determined relative to the couch 0 reference marker at physical isocenter. This approach really lets you zero in on your couch behavior without getting confused about what might be causing a less than perfect result. Next, we'll discuss the section of the report that summarizes the LINAC geometric errors that are computed via the beam axes and the couch-induced marker shifts. The front page of the report contains the innovative Z-matrix along with the vector plot for each error. The Z-matrix displays the beam-to-marker geometric errors for all gantry and couch angles, with gantry angles listed on the left and couch angles across the bottom. It highlights the maximum error at the top of the table, while errors exceeding the acceptance threshold appear in red and passing values are shown in white. The user-defined threshold is displayed below the plots. If the Z-matrix is new to you, we've included a link in the description to the 2023 Medical Physics Journal paper that introduced it, so be sure to check it out to understand the underlying physics behind this approach. The Z-matrix contains directly measured errors, which are along the couch 0 column and gantry 0 row. It also contains computed errors for other gantry-couch combinations as well. Each error represents the shortest distance of the beam axis to the marker for that gantry-couch angle combination. Just below the Z-matrix is a vector plot that gives you a visual representation of error directions and magnitudes, helping you understand the clinical impact of the errors on patient treatments. The last area I want to point out is within the summary page. Here you'll find the maximum field-to-marker error for all imported images. This can be useful if you want a more traditional approach where you're interested in keeping the maximum field-to-marker value below an acceptance threshold. Of course, keep in mind this approach includes MLC accuracy in the results, so be careful how you interpret it, since small MLC errors may lead you to think you have geometric errors, when in fact a simple MLC calibration might be all that's required. Of course, there's a lot of other data in the Isocenter Validation Report. I've just covered the most important sections. If you have any questions about the Isocenter Validation Report or anything else related to isoPoint, feel free to reach out to our support team at isoPoint@Aktina.com. Thanks for watching. Enjoy using isoPoint. See you in the next video.